Solenoid practice 2. Again, once new problems pop up on the screen, feel free to stop the video and work them on your own before I go through the answers. Below, decide if there will be attraction or repulsion between the bar magnet and the electromagnet. So once again, we're going to use our right-hand rule for solenoids, which has been covered in a previous video. Look back there if you need to, but I'm looking at this. We've got current closer to us and then it's further away. So I'm thinking that this is going to be the north pole of this electromagnet. This is going to be the south pole. That's going to be repulsion right there. How about this next case? If we have current traveling in that direction, hopefully your right-hand rule convinces you that that's the north pole, and north and south here are going to attract. How about the next case? The next case, we've got current going in that direction, so that's going to be your north pole right there. That's going to be your south pole. That's going to be attraction between that electromagnet and the bar magnet. And the last case, let's see, I'm thinking that we've got the north pole pointing that way. As your fingers curl the way the current is traveling, which is indicated here according to the positive and negative terminal, then your right thumb is going to point towards the north pole. So that's going to be the south pole. So I think 3 of these 4 are going to give attraction. Only one of those 4 is repulsion. How about number 6? Decide if there will be attraction or repulsion between the adjacent electromagnets. We've got 3 electromagnets here, and I want to know right here where my finger is and right here where my other finger is there attraction or repulsion? Once again, we're going to use the right-hand rule, and the way the current is going around this core and which way your right thumb would point, that would be the north pole right there, and that would be the south pole. Let's do the middle electromagnet. The way your fingers are curling, that would be the north pole, that would be the south pole. Clearly here, there's going to be repulsion. North and north are going to repel each other. And what is the answer going to end up with for this one? I think we're going to have the north pole being at the right and the south pole being at the left. So I think we're going to have repulsion again for both of those. Which diagram correctly represents the magnetic field lines between 2 solenoids? Well, let's see what we have here. Let's check them out one at a time. For this one here, the electromagnet is going to have a north pole at this end, and it's going to have a south pole at that end. Those field lines look okay. What about for this electromagnet? Here we're going to have a north pole at this end, and we're going to have a south pole at that end. Those electromagnets look okay, but these field lines don't look okay, do they? We're not going to go from north to north and have field lines that look like that. So it can't be letter A. How about letter B? For letter B, we're going to have current that's traveling that way. So that's going to be the north pole, and that's going to be the south pole. And what about over here? Here we're going to have this be the north pole and this be the south pole. Again, the electromagnets with their field lines look fine, but then if you have a north pole right here and a south pole right there, that's not what the field lines are going to look like right in between there. So it can't be letter B either. What about this one? Magnetic field is going to have, we're going to have north pole of the magnet right there, so that's going to be the south pole. Those field lines look good. How about here? Same thing, we're going to have a north pole there and a south pole right there, or at least close here, but no cigar. Isn't that right? Because between this north pole and this south, the field lines should point away from the north and towards the south. So I don't think that one's going to work either. I really hope letter D pans out. Let's try it. There's going to be a north pole right there. There's going to be a south pole. What about over here? The way our fingers are curling, that's going to be a north pole, and that's going to be a south pole. There we go. Now we're cooking, because the field lines between that north pole and that north pole, they're going to kind of steer away from each other. Letter D is the correct response. For the solenoids shown, the solid lines are nearer, the dashed lines are further away. Draw magnetic field lines in the figures. Note that it is the direction of the flow of conduction electrons that is shown, not the flow of conventional charge. When the conduction electron flow is shown, that means that we're going to need to use the left-hand rule. The left-hand rule for solenoids was basically the same, except you use your left hand instead of your right hand. So you're going to use your left hand, that's this one, and you're going to curl your fingers around the core in the direction that the electrons are flowing. The dotted lines are further away, and the solid lines are closer to us. So that's what we're showing here in this top picture. So in this top picture, this is going to be the North Pole, and that's going to be the South Pole, which means that through the electromagnet, the field lines point from south to north, and then outside they point, don't they, always from north to south. If I were to draw a couple of those in here, should I draw one more in there? That, something like that. I can't draw them all in. Those are continuous loops right there. How about this one? For this case, you can see that the current is closer to us, and then it goes further away. Then it's closer to us and further away. And again, we have to use our left hand here because these are represented as conduction electrons. I think we're getting something like this with your left hand, which means that the North Pole is going to be on this side, South Pole is going to be on that side. Outside the magnet, the field lines go from north to south, which means inside they go from south to north, sort of like that. A couple more and we'll be done. Which diagram shows the compass needle pointing in the correct direction? There's the North Pole of that electromagnet. There's the South Pole. Let's just do that real quick. And we're going to have this being the South Pole. That's going to be the North Pole. We're using the right-hand rule for solenoids. We're wrapping our right fingers around the core in the direction that the current is traveling, conventional current, north and south like that. And what do we have over here? Here we've got a North Pole there and a South Pole there. Clearly B and D are poor choices because the compass needle is going to have to be parallel to the field lines, and that's not what we have there. The question is it A or is it C? Well, the field lines are going to go outside and they're going to travel in that direction on the outside of the magnet, the electromagnet, from north to south. You can think of this North Pole kind of attracting to that south and the south attracting to that north. So I think we're choosing option C here. Last one. Determine which end of each wire is connected to positive and negative for each diagram. Using our right-hand rule, if the North Pole is to the right, that means you get your right finger out and your fingers must be curling like so, which means that the current is flowing from positive to negative. And how about over here? Here we get our right thumb out pointing this way, so the current is going behind the core and then it's in the front. I think we're going to go positive, negative, like so.